We have two of them. Yes, this rational function has two of them. We're going to have two of these vertical dotted lines. Yeah, we'll see. It's going to be a mess. A fun mess, though. All right, so what else? Horizontals. Now, these are more difficult to explain where they come from, but I'm going to do my best. You ready? Horizontals. Didn't we say that the horizontal asymptote told us about the end behavior? What was happening at the ends? Kind of like our left and right behavior for the polynomials. And when I say the end behavior, if I were to say go out this direction, right, that would be the right end. That would be the same as saying let x get really big, right? Let x get real big. Another way of saying that is let x go to infinity. That's actually a mathematical symbol that we use. X arrow to infinity. That means let x get huge, right? Let x approach infinity. Think about the numerator. What is a huge number times 3? A bigger number, but it's just a huge number, right? What happens if I add 5? It goes up 5. But I mean, considering how big we're talking, adding 5 doesn't really mean much, right? So when I look at this, the numerator here, I'm going to write this here so we can talk about it. 3x plus 5 is, and then on the bottom, x squared minus 2x minus 24. The numerator, hopefully you agree, really acts a lot like just x. Like multiplying by 3 doesn't affect a big number. Adding 5 to a big number doesn't really affect it. At the end of the day, the x being huge is the part that's really contributing to the size of the numerator, yes? So the numerator is like linear, isn't it? And we're dividing that by, well, let's see. We have x squared. If x is huge, x squared is a lot huger, right? A lot more huge? You got the idea, right? Subtracting this and subtracting that really don't matter. We did this before when we were looking at like degrees. We said, what does this behave like? It behaves like this. This right here, this is the dominating term of the denominator, x squared. It dominates these two because x squareds are a lot bigger than 2x's are when x is big. Do you agree? Yeah. Take 1,000, square it. How much bigger is that than 2 times 1,000? A lot bigger, right? So we're looking at the dominant terms in this thing. The dominant term here is x squared. You with me? Yes? Yes, yes. And let's do this just to make life easier down the road. Let's bring the 3 and let's bring the 1 that are in front of these. Even though I told you the 3 didn't make a difference, 3x is still linear, isn't it? 1x squared is quadratic. Okay, so we good here? Algebraically, how would that simplify? 3 on top, like we're canceling 1x, right? 3 over x. So this thing right here behaves a lot like 3 over x. If x is big, right? If x is big, this thing acts like 3 over x. Do y'all buy that? No questions?
Because you said so.
I mean, but do you buy it?
It makes sense.
If x is a huge number, then adding the 5 doesn't make a difference. Not much of a difference. And if x is a huge number, then even all this junk right here really pales in comparison to the x squared term that's out here. What's that? It's not going to matter in this example. It'll matter later, though. In this example, it's not. If this is acting like this, and this is actually this, then look at this by itself and tell me what happens when x gets big. We're starting to get into the way that calculus students have to think. What happens to this if x gets really big? So let x get big. 3 divided by, let's start letting x get big. What's 3 divided by 10? Small, right? 3 divided by 100. Even smaller. 3 divided by 1,000, by a million, by a trillion, right? Gets smaller and smaller, right? So if x is actually, if we're going to go out and we're going to let x get big, which is what we're going to try and do, right? We're going to let x get huge. Then what does this act like? It acts like this. And what does this go to? It gets small. It goes to 0, doesn't it? Eventually. Well, it's getting closer. It's never going to get there. Understand that? So what we know is that when we go out the right side forever, the function should start shrinking to a y value. See, y is the output, right? If you look at this as the function, y is the output. This output should get closer to 0. Where is y equals 0? Is it a vertical or horizontal line? Horizontal. Y equals 0 is actually the x-axis, isn't it? So I should probably have a horizontal asymptote of y equals 0, which is the same as saying the x-axis. Now, believe it or not, there's going to be a shorter way for us to do this, but I wanted us to think through it because this is the way a calculus student has to think. You know, what happens is that gets big and this one gets smaller, and you have to be able to think through. We call it in calculus number sense, just common number sense of what's happening here. All right. All right, so far this is what we've got, right? We've got one x-intercept, we've got two vertical boundaries that we can never cross, and we've got, it appears to be one dotted horizontal line that our function behaves like, yeah? Let's try and put all this on a graph right now. Let's see how good our graph would look right now if we were to just make an attempt at this. If it seems like these problems are long, it's because they are. All right, so I'm going to start with a fresh graph here. All right, I had an x-intercept. Where was it? Negative 5 over 3. So that's like, here's negative 1, here's negative 2, negative 5/3, 1 2/3, negative 1 2. So right there I have an x-intercept. So notice I'm putting a big old dot right there, okay? There it is. That's part of my picture, right? My graph does go through that point, right? It might touch, it might cross through the x, I don't know yet. What other information do I have? Vertical asymptote. I'll get to that. Let's go vertical next. The vertical we had two of them.
6 and negative 4.
6 and negative 4. So let me go to negative 4. That's right here. And what am I supposed to have here at negative 4? A vertical asymptote? A dotted vertical line, right? So this is not part of my picture. It's there to help me draw it, but this is officially not part of the picture. That is a boundary my graph cannot cross, right? And actually, as my graph gets closer to it, what has to happen? It either has to go up or down, and I'm going to have to determine which way it is. I had another one of these where? 6. All right. One more piece of information we found was the horizontal asymptote. We said y is 0, which was the x-axis. So that should be a dotted line going through the x-axis, right? But it's only our end behavior, right? It's only the end behavior. Big warning to you right here. When you draw your horizontal asymptote, only draw it at the ends. I do not recommend you draw a dotted line all the way through. That will cause all sorts of problems later. And I'll be able to tell when you take the test who actually listened to me or who went and got some tutor to help them and the tutor drew the dotted lines all the way across. It's a very dangerous thing.
Why is that?
Because you can cross a dotted horizontal line. And if you draw one all the way across, you're going to think you can't, and you're going to get yourself all screwed up. It just all the horizontal asymptote does is tells you what the end behavior is, right? In the middle is a big question mark. And
Kind of like,
yes, exactly like this, okay?
we know it's going to do this, but we don't know
We didn't know the middle. And if you draw a dotted line through the whole thing, you're going to think you know something about the middle, but you don't actually. This has nothing to do with the middle. Remember, this came from the idea of letting x get big, right? Real big. If you're in here, x ain't big, right? So that whole thing that we did to get 0, throw it out the window. Okay? Good? All right. That's all we got. That's it. Draw the picture. There are so many different things that could happen here that we're going to realize right now that we don't have enough information. So let me just show you some variations. You just tell me if this makes sense to you. I'm just going to like come in here and say, I don't know. Over here at like -6, maybe if I plug in -6, I get a positive answer. So maybe it's up here, right? Maybe. I draw it. It would have to do this, wouldn't it? It would have to eventually go down there. And then as it went this way, to the right, it's going to run into this barrier. And the barrier sends it which way?
Up or down.
Up or down. Up or down. Why not down? Ariel, you're falling asleep on me. Come on, Ariel. Why not down, Ariel? I'm going to get you involved then. Help wake you up. Why can't this function go down, Ariel?
Because there's a horizontal asymptote.
Good. Good, but no. Close, but no. What would I have to have here if I did go down and cross through? I would have to have an x-intercept. See, remember, you're allowed to cross through horizontal. That's the major danger, is that if you were one of those people who drew the dotted all the way across, if you did, then you'll think you can't cross. No, the dotted is only this. The reason why we can't turn back down is because it would require an x-intercept. And there is none, unless we screwed up the x-intercepts. But we're trusting we didn't. So do you see by a process of elimination, it would have to go up? So I would go like this. Understand? Once I do that, I must pick up my pencil. I must come over here and start drawing again. So let's go to this point right here, because this point I do know exists, right? And imagine that I have to draw it out to the left and to the right. So if I draw it to the left, what do I have to do?
Go down.
Do I have to go like this? Would this work?
Yeah.
That would work, right?
Because it has to, because there's no more x-intercept.
There's no x-intercept, but could I have done this?
Yeah.
I could have done that also, right? So which one is it? See, this is what I'm saying. There's a lot of shit that we don't know right now. There's still stuff we're not clear on, but that would be okay, right? That would be all right? Now look to the right. If I start drawing this to the right, I could go up, or I could touch and come back down, couldn't I? I could. I'm going to go up because I'm guessing. All right, I'm guessing, and then it's going to go like that. Would that work? That's still satisfying all my requirements? And then over here, I'm going to pick a point down here and go like that and go like that. Would that blue picture represent a possible answer?
Possible.
Possible, right? It's possible. Do y'all understand that? That this has the horizontal asymptotes I need. It has the verticals I need. It has the x-intercept I need. I'm in business. But there's no telling if that's it or not. Do I have green in here? Is there a green? Oh, yeah, let me grab. You want to throw one of those to me? All right, let's go. Oh, well, I almost blew that one. Okay, so this would have been also an acceptable answer. Would that green one have also satisfied all the requirements?
Yes.
So, and then you could do a bunch of other stuff too.
Like cross through the
Oh yeah, I could have come down like this and come like that also. So see all these different variations? So with what we got so far, which was three things. We got x-intercepts, we got vertical asymptotes, and we got horizontal asymptotes. As you can see, that is not enough for us to be able to nail down exactly what this function's doing. So we have to do one more thing, and it's a little bit tedious. What we're going to do is we're going to test some points. All right, we're going to test some points. So let me erase all this in here. I'll keep the stuff that we do know for sure. What the heck? This point's here. we need to test some points. How about a point, if I tested a point somewhere over here, and notice I'm going to use a little x for it and not a dot, because I don't want you to mix it up with an x-intercept. Let's say I test like -5. That's going to spit out a positive or a negative number, isn't it? If it's positive, I'm up here, right? And then it must do this, right? If it's negative, I'm down here, and then it must do this. So just this one test point should be able to help me get this piece, shouldn't it? Yeah? So I'm going to test just that one point. I'm trying to figure out how many test points am I going to need. How about over here?
Well, I would do at least 0 because you kind of figure out.
I can figure out. Let's move left to right. Should I get something in here?
Yes.
Yeah, maybe -3, because if -3 is positive, it's up here, and it goes like that, right? And if it's negative, it must go like that, right? So I should have one there also. Now, should I get one over here somewhere? Okay. You could go with 0 or any of these, right? Let's say 1.
With the 0 and
Let's say 1.
y.
If it's positive, what? Then it goes up. If it's negative, then it would come down, right? Do I need any more in here? I don't need any more, right? I mean, I could do another one, but I don't need one. Do I need one over here?
Yes.
Yes. So that I can determine if it's up or down, right? So how many test points did I need? 4, right? How many verticals did we have? How many x-intercepts did we have? You'll always need one more test point than the total of your x-intercepts and vertical asymptotes together. All right? So if you have 2 verticals and 1 x-intercept, that's 3, right? 2, 1, that's 3. You'll need 4 test points. If you have 2 verticals and 2 x-intercepts, you'll need 5 test points. If you have 3 verticals and 7 x-intercepts, you'll need 11 test points. Understand? The rule of thumb is 1 more than the total number of x-intercepts and verticals combined. All right, you ready to plug these in? We get to plug these in where? Into the original function. So let me write that down. We've forgotten what that is. The original function
3x plus 5 over x squared minus 2x minus 24.
That's f of x. And I get to plug those in. So let's plug in -5. Let's have the pleasure of doing this. That's 3 times -5 plus 5 over, oh my goodness, are you kidding me? -5 squared minus 2 times -5. This is starting to feel like torture. Numerator is -15 plus 5, -10 over 25 plus 10, right, 25 plus 10, 35 minus 9, minus 24 is what? 11. Should get 11. You got this? And then now that's a decimal, right? It's -0.9 something. 909091. Okay, -0.909. Good enough, right?
1. Close enough.
What was the most important thing for us? What did we really want to know? If it was positive or negative, right? And it's negative. So really, remember with polynomials, we didn't know how high they went and how low. We said we'd save that for calculus. Same thing here. I don't really care how low this goes. I'm just going to put a dot down here. Doesn't matter to me. And because of that, because I don't care how high or low it is, there's actually a shorter way to get this answer. Would you like to see a shortcut? Everyone always loves shortcuts. Now look, does everyone understand that you could continue to do this for the remaining 3 points? Plug -3 in, plug 1 in, plug 7 in. Everyone should be able to do that. But if you just want... Pardon? Yeah, positive and negative, just plot them. But let me show you an easier way to figure out that this would have been a negative number, all right? Without having to plug it in. Well, like this. So what I'd like for you to do is I'd like for you to rewrite the function but I'd like for you to write it factored. So remember we factored the denominator earlier? It was x minus 6, x plus 4. Now I'm going to point out that we have now, when we factor, we create multiplication, don't we? This is multiplication right there. And the top is its own factor. What I'd like for you to do now is plug -5 into this instead. So watch how fast I'm going to be with this. What is 3 times -5? -15 plus 5? -10. It's a negative number, right? Okay. I'm just going to put negative and circle it on top. I have a negative number on top. Right here, plug in 5 minus 6, or sorry, -5 minus 6. -5 minus 6 is -11, right? That's a negative down there. Times, what's -5 plus 4? -1? It's a negative number. What's a negative times a negative on the bottom? Positive. So this is a negative number over a positive number. What's negative over positive? It's negative. So I got a negative answer without actually having to go through the mechanics of this. Do y'all see that? It's a little faster, and later on it's a lot better when the problems get uglier. Why could you not do that here? Why couldn't I just say, okay, that's a positive number, and then over here figure out, why can't I do it there? It's addition and subtraction. You can't tell me, right? Do you all agree with that? If I tell you I have a negative number, and I subtract from it a negative number, can you tell me what the answer is? No, because you don't know how big these numbers are. But if it's multiplication, which this is, then you can determine it a little quicker. All right, you want to see if I can convince you that that's worth doing it that way? Let's try -3. What's f of -3 into this? So see how quick we can go. 3 times -3, -9 plus 5, negative over. -3 minus 6, negative. -3 plus 4, positive. Okay, bottom is negative, top is ratio of negative over negative, positive, guaranteed. There we go. We got a point up here somewhere. With me? And you keep doing this. Now I'm not going to do the rest. I'm going to let you do that on your own. But I'm going to tell you what they are. I'm just not going to work them out.
So we're only going to use one more point more than the x-intercept and the
Vertical asymptotes combined. Yes.
What the bottom doesn't factor.
If the bottom doesn't factor, well, then you'll have to do the old way of just plugging in. All right, so we had when we first did our first test point, we had a negative. Then we got a positive. Our next test point, if you do it, you'll get a negative. And if you do the last test point, you will get a positive. All right? Hey, they switched. Did y'all notice that? It was negative, positive, negative, positive. Maybe all I have to do is find the first one, and then after that, it just switches. Nope. You have to check each one, sorry. Sometimes they don't switch. All right? Any questions? Now, with this information, there's only one drawing possible. So let's start at the first point that we know for sure exists, which is this one. If I draw that out to the left, what has to happen? It's got to go towards that horizontal asymptote, that magnet that pulls my function up. As I draw it to the right, it's going to do what? What is it going to do? Towards this, and then when I get to it, don't touch it. So what do I do? Just stop? What do I do? Okay, go down. So you want me, why not up? I don't turn up because I don't have an x-intercept, so it must go down like this. All right, good. That part's done. Now you go here, pick your next point that you know exists, draw it to the left and to the right. So tell me about going to the left.
It's going to go all the way toward -4, but up.
Up. So let's just say up or down, okay? Because we know we're going towards the vertical. We'll just say up or down. And if you want to be even more technical, we can say it's going to infinity or negative infinity. All right? So it's going to go towards infinity. Why not go down to negative infinity?
No more x-intercept.
You would have to cross through the x-axis. You don't have an x-intercept there. Okay, now look at this. The good news is that the next couple of steps is back in like first grade, even before first grade. This is like connect the dots. Look, there's nothing in our way, right? No verticals, no horizontals. I've got to get from here to here, from there to there, right? So just connect them together. Okay, once I get here, what?
It's gonna go negative.
Keep on drawing this way. Oh, there's a barrier.
Negative infinity.
Up or down? Negative infinity. Why not up?
No more x-intercept.
Don't have an x-intercept up here, right? So it has to go down. See, it's a process of elimination. Finally, on this side, to the left, up, to the right, flatten it out. There it is. That's the graph of your, that is the graph of 3x plus 5. And this is actually it, okay? That's the precise computer graphed version of it.
Close enough.
Right? What, do you remember with our polynomial functions? I said the things that we want to be able to do in this class is figure out where the polynomials hit the x-axis. We want to know where it's above or below, right? How high it goes, that's a Cal 1 problem. We don't do it here. Rational functions, same sort of thing. I want to know where the function is above or below, right? It's below the x-axis here, isn't it? It's above right in here. It's 0 here. It's below over here. And it's above over here, right? So I can get the same sort of information I was doing for polynomials. If you want more detail than that, you go and you do calculus. So that graph, as good as it is, mine is just as good if all we're talking about is where is it above and below and where the x-intercepts, right? Where are the vertical asymptotes? I can tell you that tells you, I can tell you, right? So we're happy with that?
So how would you rank that? Where is it above?
Okay, so
Do we have to put it in?
no, it would be interval notation.
Like
Yep.
infinity to-
If you wanted to know where this function was positive, greater than 0, it would be between -4 and, what was this? -5/3. Where else? Unioned 6 to infinity. That's where this function is above the x-axis, right? From here on, it's above, and between here and here, it's above. Now, I'm not going to ask that, but that's something we could ask, right? What do y'all think? That only took like 40 minutes.
It's a lot of work, but I mean, it's
That's the first problem, you know. Yeah, it's not that they get harder, it's just there's some different variations that we can have here. What if you go and you start the problem out and you're trying to find the vertical asymptotes, so you go set the denominator equal to 0 and it doesn't factor. Then you have to use the rational zero test. You have to create the list of numbers. You have to use synthetic division, and you break it all down. Now that sounds like a test problem, you know, where you're pulling out all the stuff, right?
That sounds like a calculus test problem.
All right. I probably won't do that too. Well, I don't know. I'm not going to make any promises yet. How about your next test, just one problem? Just one of these. It includes everything.
Is that just the only problem on the test? 40 minutes. So each step is like-
Yeah. All right, so should we talk about a process? Let's talk about a process. Oh, some properties. We've already talked about that. Here's how to sketch them. Look at that's the process. That's everything I just said,
this is a lot easier
written down.
than that.
Well, I'll go through this process in a second. We do have one other thing we do need to worry about, all right? A hole, all right? We haven't talked about a hole. So let me give you an example of something with a hole. Look at this function here. We'll do this one next. All right, so I'm gonna refer to the steps now. Let me blow this up so you can see this. Whoa, there we go. First step, make sure it's a rational function. So is this a rational function?
Yep.
Yes. Completely factor the numerator and denominator. That's the next step. Because that helps us later, right? So we factor everything out. So I'm just going to rewrite this factored, which is, if it factors, x minus 3x plus 2. You agree? The bottom, x plus 2, x minus 2. You agree with that? Okay, so look at part C. Look for common factors. If you have them, cancel them out, but remember, you will have a whole at the value of x, which makes those factors 0. So let's take a look at this. If I factor this out and cancel, I need to remember to set that factor equal to 0 and solve for it. And remember, I will have a hole in my graph here. Let me illustrate what I mean by this, all right? We haven't talked about a hole, but let me illustrate. Let's, and just put this on the back burner for just a second. If you were to get your graphing calculator out, and I were to ask you to graph 1, what it would do is it would spit out this graph. Here's the little calculator screen, and it would spit out a little graph. It would draw it, and it would go like this. Like that. Straight across, 1 unit high, it would graph it, right? If I were to also ask the graph, or the calculator, to graph another function, g of x, to be x over x, what would it draw? Yeah, so like plug in 1. What do you get? 1 over 1 is 1. 2 over 2 is 1. 3 over 3 is 1. 4 over 4, right? So it would draw the same graph. What's the difference between the two graphs, though? There is a difference. Your calculator's not going to show it to you, though. What's the difference? What's the domain of this function? What's the domain? What can I plug into this? Nothing? I can't plug? If I plug 5 in here, what does it spit out?
1.
If I plug in 10? Pi?
1.
Negative 5?
1.
No problems. All real numbers. What's the domain of this?
X.
Can I plug anything I want into this?
Yeah.
What can I not plug in?
0.
0. 0 divided by 0 is undefined. So believe it or not,